minus 3 will give you this guy. Correct? A UT will be like that. A UT minus 3 is like that. This and at this becomes just the rect. Why I use UT? Because you're given the Laplace of a UT. Alright, so your XS so your XT right? That will give you this guy here. Correct? So if you want to find the response, from here, right? Sorry. E to the okay. Right. So if you're already given this guy, so you got this guy. Substitute in, you got ys. Inverse Laplace transform, you get yt. Yeah? Follow? Okay, so I show you the solution. You were asked to sketch as well. You are asked to sketch. Alright? You are asked to sketch. So what will happen is this. Basically, we have an integrator there, right? GS is an integrator, 1 over S. It's just that it's delayed, right? Huh? When you substitute everything inside here, what you will find is that as an integrator, basically it will charge up until here. Then you turn it off, we flatten out. Right? Huh? You charge it up and then you flatten out. That's basically it. So that would be okay. So that's your XS. So your YS is GS. Alright? Work it out. That's your YS. So you sketch it, this is what will happen. The actual solution is this is actually, if you ask me, I did say this question, but if you ask me, this is actually not correct. Why? You know why? Because in the original, you see that there is this term there. He didn't take that into account. So there's actually an E term here. You follow? There's an E term there. What it means is that the response will not be this guy, but everything shifted, it will go up like that. From here, 3 seconds up. Everything is shifted to the right by 3 seconds. Not from 0.
So if we draw it from 3 seconds onwards?
From 3 seconds onwards. Everything is shifted. Got it? Because he did not take into account this guy here. See, it's missing. Can you see it? The e to the minus 3s is missing here. Alright, so everything is shifted by 3 seconds. Got it, everybody? So if you're taking this down, please note, it should be from 3 seconds onwards, not from 0. Not from t equals 0, but t equals to 3 seconds. Okay? Any question? Okay, Alright, question 2. Okay, the signal xt, which is sinc squared 2t, is sampled at 8 Hz. To produce the sample signal xs, derive the expression for xs. Okay, that's straightforward now. Huh? Okay, sample. So you got xt, which is sinc squared 2t. So xs is xt multiplied by the co-function at 8 Hz. That means k over 8. Okay? Right? So you substitute inside here. Which right? Okay? So that's the expression for part A. Everyone with me? Any question? Then Fourier transform. Okay? Fourier transform, I'll come back to here first. Because xs, if xf convolve with this guy, alright, so you replicate this at multiples of 8 Hz. Yeah, at 8 Hz, at 16 Hz, at 24 Hz, etc. Okay? What is xf? Sinc squared if you try. Correct? So the try will go here, and you convolve it, becomes a periodic here. Because this guy is actually this. Sorry. Okay, so this is a try. Got it? Everyone? Sinc squared is try, huh? So that's the second part. And of course you draw it, you will have your triangle at 8, 16, 24, 32. Because it's replicated by this guy. Good? And marks. Okay, everything is there. So the try, you can see the try is there. Right? Okay, you replicate. Alright? Any questions? Everyone okay? I go to question 3 now. Ken? Question 3. Energy signal xt is given as follows. Alright? It's e to the minus pi t squared. Determine the energy spectral density, ESF or XF. Okay, straightforward. Inside your Fourier table, if you look at the end, Alright, I'll go at the end. See this guy here? Right? We have e to the minus pi t squared. Yeah? So this is his Fourier transform. That means pi is 1 over a squared. Yeah? In your question. Huh? You have e to the minus pi t squared. So pi must be 1 over a squared. So wherever you see a, you can substitute already. If pi correct? So the Fourier transform is given already to you. So if you're given the Fourier transform, that means you know xf, capital Xf, the energy spectral density is mod capital Xf squared, right? So you just power 2. Okay, so that's the first part. Part A. Huh? So that means you know this guy, you change it to XF, then you want EXF. Okay? Okay? Just put it in. So part A is done. Part B, find the 3 dB bandwidth. 3 dB bandwidth, that means right? That's 3 dB bandwidth. So you already found the formula for this guy. Change f to f3 dB. This guy is known when this is 0. It's a number. Substitute, the only unknown is 3 dB, ft 3 dB. Solve for f3 dB. Okay? Last part. In computing the total energy of xt, would the time domain, let me put it back to the question. In computing the total energy of xt, would the time domain or frequency domain approach lead to a simpler solution? So, we have the Rayleigh energy theorem, right? Correct? Alright, so the Rayleigh energy theorem is such that we calculate E as integral either one, right? Okay, so we already know this guy. This guy is the E term. You'll find that this guy is also an E term. So no advantage. Both also same amount of work. Both of them are E term. Right? Okay? So no advantage. So same. Same thing.
Misleading question.
Huh?
It's a misleading question.
Nothing misleading about it. Same thing. Alright, so that's the answer. So let me show you that answer. Am I going too fast? Are you okay? If I'm going too fast, you have to tell me and then I'll stop. I'll slow down. Yeah. So you can see, first part. Alright, that's the Fourier transform pair. And I told you alpha squared is 1 over pi. Alright, so you find that in that case this is xt, therefore xn is this guy. So it's root pi divided by root pi become 1. This become root pi 1 over root pi, sorry. Okay, so one of the pi will cancel, you will get this in f squared. So energy spectral density is this square, which is this guy, so you got a 2 in front here. Because it's square, you got 2 in front. Then this one is what I showed you here. Alright, substitute inside, you can find B, which works out to this. Rayleigh theorem is time domain, frequency domain, same pain. Alright? No advantage.
So,
yeah.
Part C, do we need to do a...
No, he didn't ask you to do it.
So I can just explain that concept.
Yeah.
By the theorem, both also can.
Yeah, same.
Okay.
Huh? Okay? No advantage. If he asks you to, if the question asks you to derive it, you derive it. He didn't ask you to derive it. He's just asking you whether one way is better or the other way is better. Is time better or frequency? So as I said, same pain, right? Okay. More positive is both equally easy. Huh? Okay? Yeah, so that's question 3. Everyone okay? Okay, question 4. Alright. So the pole zero diagram for two systems, system 1, system 2, are shown in figure Q4. What is the damped natural frequency, undamped natural frequency, and damping ratio of system 1? System 1. Okay. So if you look, the axis is here, the imaginary axis is here, the real axis is here. So these two guys are complex conjugates. It is at -3 plus or minus J1, as you can see. This is 1, minus 1, correct? -3 plus or minus J1. Now, if you go back to your notes, you will recall that when I draw my poles, okay, if these are my poles, this value here is sigma theta omega n, right? That is the value here. Okay? These are my poles. So that's that. You will also know that this is omega d, correct? And this length here is omega n. It's testing you this. Yeah, it's in your notes. Omega n is this one. Zeta is this line here, this point here, minus. Alright, so you're told this guy is -3 plus J1 -3 minus J1. Okay, so that means zeta omega n is 3. Okay, omega n is 3 squared plus 1 squared, because this is 3, this is 1. Okay, omega d is 1. So he asked you for this, he asked you for this, he asked you for this. So all solved already. That is what was testing you. Okay? Huh? So that's part 1. Part 2. Following a step change of magnitude 3, the steady state output of system 2 is 15. Okay? Derive the transfer function for system 2 using the pole 0 diagram and the steady state information. Okay? So, you're already given the poles for system 2. So if you look carefully at system 2, these are the poles. So it's at -2. Again, this is the real axis. This is the imaginary axis. So it's -2 plus or minus J2. You see, J2 here, minus J2 here. Those are your two poles. Alright? So that means system 2 looks something like this. Right? Those are two poles. Yes? Which you can clean up now. Alright? And he told you that the steady state output for a step change of magnitude, that means it's telling you xt is 3 ut. It's a step change of 3. Therefore, you know xs, right? Correct? gs is this, xs is this, and then he told you in steady state is 15. So from here you can find ys, right? Okay? And it says steady state is 15. That means so the only unknown is k. When you plug everything inside here. Got it? So you can solve for k. Then you can get the transfer function. So that's part B. Any question? Huh? So I'm just using the information given to me in the question. Huh? Okay? Anyone not clear? Okay, last part. Suppose system 1 and 2 have the same DC gain. Will system 1 or system 2 exhibit a larger overshoot following a step change in the input signal? Okay, now this one, what does the overshoot depend on? This one you have to know. What is the parameter that determines the overshoot? Is it omega n, is it omega d, or is it zeta? Zeta, right? The larger the zeta, the larger the overshoot. Now you already found the zeta for system 1. Can you find the zeta for system 2? Cannot, because you know where the poles are. And you see which one is bigger. Okay? Huh? Alright, so it's there. The first part, alright, omega d, omega n, find zeta. And this is the guy, k, and you work it out, you find k is 40, so the transfer function is this guy. Okay, and overshoot. System 1 will be smaller than system 2 because the damping ratio for system 1 is larger. Okay, it's the other way around. Okay? Okay, huh? So that's question 3. That was question 4. Alright, so okay so far. So come to question 5 now. Looks familiar?
Yes. Assignment.
So a space booster in figure Q5 has a transfer function as shown, where capital Phi and capital F are the Laplace transform of little phi and little f, respectively. Okay. Describe what happens to the space booster when it is fired up with Ft equal to delta t, that this is an impulse, where delta t is the unit impulse function, and sketch the impulse response. So if Ft is the unit impulse, that means, alright, then the response is just equal to the Gs. Alright, because if this guy is the same as delta, the capital F is 1. Capital F is 1, so the response is just equal to Gs. And if you do the inverse of this, what will happen? Alright, you can factorize it. You get 2 factors. You will get one positive E and one negative E. What will happen if you have one positive E and negative when t tends towards infinity? The negative E will tend towards 0, right? E to the minus infinity is 0. But the positive one, E to the infinity, will be infinity. So it will shoot up. That's the response. Because you're supposed to sketch it. Okay? That was the first one. Any question? Second part. So, part B. A control system is then developed for the space booster such that the overall closed loop control system has this transfer function. Okay? If KD is 0, so if KD is 0, this is 0, huh? What is the minimum value of KP required for the closed loop system to have bounded output? Okay, by the way, any more submissions? Any more submissions for assignment? No?
Just solving the assignment now.
Okay.
Same.
Ask you a question. You know. Okay, if KD is 0, this is 0, right? So you get S squared plus KP minus 0.04. What will happen? Where are the poles? Will there be a pole on the right hand side? Do you think there's a pole on the right hand side? Because if there's a pole on the right hand side, it's always unstable, right? Okay? The answer is yes. There's always a pole on the right hand side. Why? Because of this minus sign. Okay? Because of that minus sign. So that means, for this part of the question, you will never be able to get a bounded output, which is what you have in your assignment now. Right? Your assignment has 3 parts. One is when is it become a second order system? That one you all got correct. Ki equals to 0. Yeah? Second part is what happened when Kd is 0 and Ki is 0. Third part is what happened when Kp is 0 and Ki is 0. Okay? So second part is, no, you will never get a stable system. That's part 1. Now what happens if Kp is 0? If Kp is 0, so have I got it right? No, sorry, the other way. When Kd is 0, you will get this. So the only way that you can have a bounded one is this constant Kp minus 0.04 must be positive. Must be positive. means Kp must be at least equal to 0.04, greater than 0.04. Okay, sorry about that. Okay? Huh? Right? Because we don't have this guy anymore. So it's just a constant here. So it must be s squared plus something, not minus. Because once you have s squared minus something, one of the poles is on the right hand side. It has to be plus. And the only way to get it plus, Kp must be greater than 0.04. Alright? Okay. Third part. If Kp is 0, this one cannot find stable because of the negative sign. That is what I mean. Cannot. Okay. Now this one is design Kp and Kd so that the closed loop system has this pole. Okay, straightforward. You already told the poles. The poles are already given. So you can find the denominator, right? Because the poles are given. Once you find the denominator, you compare the coefficients, s squared coefficient, s coefficient constant, then you will find the rest. Okay? You already told the pole. Alright? So since you are given the poles, then what you have is that your closed loop system S plus 0.2 plus 0.3j bracket S plus 0.2 minus 0.3j. Work it out. Okay, clean it up and compare coefficients. That's it. That is part 3. Okay? Okay, final part. Find the damping ratio and the undamped natural frequency of the closed loop system with poles of this number, of these two guys. Very simple. Remember, generic form s squared is equals to 2 zeta omega ns plus omega n squared. Once you clean it up, you compare the coefficients. You can find omega n squared, which is the constant. Omega n squared is the constant. And once you find omega n, the coefficient for s is 2 zeta omega n. So you can find zeta. Right? Okay? Does it make sense? Step by step. Right? As I said, the generic system remember this? Okay? So you can find all this. Once you open this up, so let me just show you. So that's question 5. That's it. No more again. It's quite long. Put everything in one go. And you're also supposed to sketch the impulse response. So of course you know that it will oscillate and then die out. That one you know, that's the second under damped system. Okay. So what I'll do is I will show you up to here first. Alright, I'll go through very quickly. So you can see that from here you can factorize it. So those are your two poles. Alright. Okay. And if you see, you can get these two, right? The two exponents. When t tends towards infinity, this is 0. When t tends towards infinity, this is infinity. So if you sketch it, which is not drawn there, so when you draw it, it will look something like that. Okay? So it's not drawn. Then the closed loop system is this guy. When KD is 0, you got this. Therefore, this must be positive. So KP must be greater than 0.4. So that's the second part. Right? And when KP is 0, you got this. Because of this negative sign, you will always have a pole on the right hand side, which means it will never be stable. Okay, that was that. Okay. And then this part, as I said, you're already given the two poles. When you open this up, you got this. So this guy must be KD. This guy must be KP minus 0.04. So you can calculate for KP. Yeah? I tell you what, will someone want to quickly click here first? Because I don't need this, I have that later. Okay? Alright, as I finish, I'll pass it up. Then you can. Faster, the other day, waiting for my paper bag, you want to go to the think lab.
哦，那拍那个。
Alright, okay, and then the last part is this part over here. Okay, so it will have a damping ratio, damping thing. Okay, and you will find that it will stabilize at 0. Okay, 0. Why 0? If you look back at the expression here, okay, say it's an impulse response, right? So if you do the limit of S times this, when S times what 0, you get 0, right? Huh? Because your GS is this guy, your GS so impulse, substitute, you get 0. Okay? Huh? Yeah? Which is not shown here.
Which part is this part, sorry?
Yeah?
This is which part?
This is this guy here. This steady state value. 0. 0. Huh? Do you all follow me? So if you substitute this guy inside here, you still got an S in the numerator. You said it's 0, it's still 0. Huh? Okay, there's an S in the numerator. Yeah? So that's question 5. Okay, then we come to question 6. I assume that you are able to follow my pace right now. If you can't, please, you have to stop me. Okay? You don't stop me, I assume that you are okay. Next, consider the periodic signal xt shown in figure Q6, which comprises periodic Gaussian pulses. Okay, you have periodic Gaussian pulses, so that's a Gaussian pulse, given by e to the minus t squared over 0.25. Okay, all right, and it's repeated. Actually, there's a every 4 seconds. You can see every 4 seconds, 8 seconds, etc. Derive the Fourier transform of capital XF. So that's pretty straightforward. Okay? How? Remember, always decouple this into the generating function, that means 1 pulse only. Now convolve with your home function to get the periodic signal. Got it? So in this case, you have xt, which is the summation of alright? So what's the generating function here? The generating function is that's the generating function. That's your Gaussian pulse, which is being repeated. Because if you convolve inside that, you get this guy. Right? So this one, Fourier, if you look at your table, there's a table there for Gaussian pulse. Let me fill out the table. Thank you. Alright? So, you know your table. Gaussian, okay. So that's your Fourier. So if you compare against this, a squared is 0.25, right? Huh? Correct? Okay. So now if you do the Fourier, Fourier transform of this guy is this. A is 0.25. Guy here, Fourier becomes this guy. Convolution becomes multiply. This one you get 1/4. Okay? Multiply. So wherever you see f, you replace by k/4 by bringing inside there. So you can get 1/4 is here. This half, that means 1/8 root pi. This one you can clean up. It's pi squared over 4. Okay? So you need to be able to break this guy out so that you can do the Fourier. Huh? That's your generating function. Okay? At the back? Yeah. How to break? Because you see, this is a repeating pulse of this guy. At 4 seconds, at 8 seconds, at 12 seconds. Right? That's what this is telling us because of the summation. Okay? If you still cannot see it, if you still cannot see it, okay, this guy here, let me take when k is 0. Okay, when k is 0, I will get e minus t squared over 0.25. When k is 1, e 1, t minus 4. When k is minus 1, etc. That's my generating function. That's the pulse of this guy. Can you see now?
The delta should be s minus 4k by 4 the whole square, no?
Where?
Here.
Which one?
Can you explain the last guess?
I just replace wherever f by k over 4. There's a square. Which one? Which part? Yeah? So, when you pull it out, you have a generating function. This guy is just one pulse. I replicate it at this comb function. This comb function has a delta at t equals 0, t equals to 4, t equals to 8. When you replicate, you will get this periodic signal.
Backward replication.
Okay? Huh? So that's my generating function. Okay. I backtrack. Suppose I have a waveform. I call my waveform, this is my waveform, huh? Let me call my waveform x naught t, which is this guy. Okay? And I generate a signal, which is x naught t, convolved with a comb function. I convolve, huh? What will happen? I will get this guy, 4, I will get this guy, 8, I got this guy, minus 4, I got this guy, minus 8, I got this guy. That's what I'm doing here. X naught is this guy here. Convolved with the comb function, I get this periodic signal. Okay now? Alright? The rest okay? Huh? So you need to be able to see all this, you know? Alright? I mean, we've been doing this, I don't know how many times already. You know, we're very boring people. We keep repeating ourselves, you know? Do you realize that? Huh? Huh? Do you realize that? A periodic signal is obtained by taking one pulse and repeating that pulse at the periodic value. This is a periodic signal. That's what it is. Which is what this formula is telling you. The original pulse is x naught, which is this guy. I'm repeating it. So I convolve with a comb function. Okay? So we have found part 1. Derive the Fourier series. Fourier series is what? Bring everything inside here. my Fourier series coefficient. Yeah? Okay? So that's part 2. Part 3. Derive the expression of the average power. Very simple. You already found your CK. What's the power? Mod CK squared. Sum of mod CK squared. Huh? Power. So power. That's number part 3. Okay. Last one. Let the n harmonic of x be the harmonic that is closest. Again, we saw this before. Closest to the 98% containment bandwidth. Explain how n can be found. Okay. So we already found P. All right. You want to sum for the 98%. You sum up to the nth harmonic, and that must be equal to 0.98p. That's what you want. Up to the nth harmonic. Sum up to the m, not to infinity anymore. Up to the m gives you this. Got it? So that is question 6. Are you all with me? All right, so let's have a look at the answer. Okay, so that's the first part. Right? So you can see, so I broke that thing out with this home function, and then the rest, Fourier transform of this guy is here, Fourier transform of this guy is here, clean it up, you got this guy. Fourier series coefficient is we bring this inside, plus this one, therefore there's a Fourier series coefficient. Average power is this, okay? Are we supposed to do 3 dB then? Did I miss out 3 dB value?
No, there's no 3 dB value.
No, the question didn't ask for 3 dB value. Okay, I think I must, they must have changed the question somewhere. This is probably an older version of the answer sheet.
Oh,
Okay, so that's the one we want, because this is the 98%. This is based on a question where you're finding the 3 dB value. Okay, so you can do both. Okay, that's the one that you're looking for. I opened it in the correct version. So that was question 6, right? Then we go to question 7. Okay, question 7. Radio station X transmit the signal 10 sig 10 t cos 2000 pi t, and radio station Y transmit the signal yt as shown. So it's a signal X and signal Y. So signal X is actually this sig function times cos. And at what frequency? 2 pi ft. So f must be 1000 hertz, right? Okay? So if you do the Fourier transform of this thing become a rect. So you get a rect that is at plus and minus 1000 hertz. Right? Because it multiply here become convolve because the cos gives you 2 delta function. Convolve with 2 delta function at plus and minus 1000 hertz. So you get a rect here, you get a rect here. Okay? The second guy here has a signal M, where the spectrum of M is given by a tribe. Okay? And the tribe is plus B and minus B. That's the message. Okay? Plus B and minus B. Okay? And of course is centered at plus and minus FC, wherever FC is. Okay? So, and FC is much greater than 2B. So radio interference between the two stations will occur if the spectra of their transmissions overlap. Okay, so question 1, part A. Sketch the spectrum XF of X. I already explained, right? Rect plus 1000 and rect at minus 1000. Okay. So part 1 finished. Suppose B is 8, that means 8 hertz. What is the range of FC values that should be avoided by radio station Y so as to avoid radio interference between the two stations? Okay, right? So let's pause that. Okay, so for X, we were told that XC can sync and be alright, so that means XF right? So that will give you so you draw the spectrum. Width of 10 only, okay. So this is your XM. Correct? Okay. So this one is a width of 10, so it's 995 to 1005, okay? This is a width of 10. 995 hertz to 1005 hertz. Yeah? 10 hertz width. Okay? Okay? So that's part 1. Part 2 is you're told that B is that. So now let's look at Y. Okay, let me do a different color for Y. mt cos 2 pi fct. And of course, m is supposed to be tri. Okay, so this is tri. So YF will be MF on ball F minus FC F plus FC, right? And this guy is a tri F over B. Okay? Convolve with that. Let me shortcut that. Okay, so if you draw this guy now, the tri has, looks like that. So here will be right? That will be your YF. Do you agree? Okay? So if these two, the red and the green, are not to overlap, okay? Then this region is where the green has to avoid. The green can be anywhere from here onwards, which means it's anywhere from here onwards, but not less than. Because the less will overlap, right? It can also be anywhere between here and here. Agree? So, since this is, we know this one, this is 1005, right? Okay? FC is here, and this is B, right? From here to here is B. Correct? So if it's on this side, it will have to be at least this 1005 plus B, isn't it? Then you're okay. Or 995 minus B, also okay. Okay? That is the range. So this is the no trespassing zone. Agree? So that's part B. Part B. Everyone follow me? Then part C. Suppose FC is 1020. 1020 hertz. Find the maximum value of B that can be used by radio station Y. So now let me just clean this up a little bit. Let me remove that. So it says now FC is 100. FC is 1020, right? So if it is 1020, let's say it's here. This is 1020. This is the maximum B that I can do, right? This is the maximum B that I can do, right? Okay? What is this? This is 1005. So from here to here is 1020 minus 1005, which is 15. That's the maximum B. So that they don't overlap. Make sense? Everybody? Okay, so that's part C. Part D. Suppose YT is sampled to form YST. Suggest a sampling frequency fs so that MT can be recovered without distortion by passing YS through a suitably designed low-pass filter.
Because your laptop is going to.
Why is it blinking like that? Huh?
它这个猫。
Strange things happen. Okay, so it says, what is the sampling frequency that can, okay, suppose YT example suggests a sampling frequency fs so that MT can be recovered. MT can be recovered with a suitable low pass filter. Now, if I want to have a low pass filter, look at this signal. This is my YS right now. It's not in sample yet. Sample will replicate this, right? At the sampling frequency. Replicate Fs, 2Fs, 3Fs, etc. Sampling. Agree? That's sampling. So if I have to recover this with an ideal low pass filter, I must have a triangle in the center here. That's my MF one. That's my original MF. Right at the top. MF is tri F over B. I must have a triangle here, right? Otherwise I cannot recover it with a low pass filter, isn't it? Do you agree? Huh? I must find a way such that I put something here, otherwise I cannot recover with a low pass filter. So how can I put something there? Well, you can do it if your Fs is the same as Fc. Because if I take an Fs, which is Fc, I replicate it at Fc, I will get this guy here. I replicate this one, it's just that it will be double. I can recover, but the amplitude will be scaled double. Follow me? Does it make sense to all of you? Okay? Right. So that's part D. Question 7. Any question? A bit tricky, right? Huh? A bit tricky, huh? Okay? But once you understand the logic behind it, then it's easier. Huh? Okay? So as you can see here, this was SF, which I drew over here, and then this is the diagram that I drew over there just now. So all of that are inside. All right. Okay. So that's the range. Less than this, greater than that. Okay. And then the second part is this part. Found that it was 50, as you can see here, 50, 50, and then you recover it, get like that, okay? If your Fs equals to Fc, then you can recover it with the low pass filter. Okay? Any question? Yeah, pass it around. So that's question 7. It's the last one now.
18挺难的。那下个就不容易了。我准备做18题了。
So this question is a bit long.
这个就是移动的。
Right. most loudspeakers are not capable of covering the entire audio spectrum with negligible distortion. Consequently, most hi-fi speaker systems use a combination of loudspeakers, each catering to a different frequency band. Filter systems are used to split the audio signal into frequency bands that can be separately routed to loudspeakers optimized for those bands. That is, a low-pass filter is used to isolate signals for the woofer loudspeaker, and the output signal of a high-pass filter drives the tweeter loudspeaker. Derive the transfer function of the two filter circuits shown in figure QA. This is a key question, this part. Why? Because the circuits are so simple. Right? So if you look at the circuit, this guy is just an RC circuit. We've done RC circuits, it's a first order system. So what is, I ask you to do the transfer function. You want to find out V out over V in. Alright? Now, if you use complex impedance, it's very straightforward because the voltage across this resistor is this divided by this plus this. Correct? The complex impedance of this guy is 1 over SC. The complex impedance of this guy is R1. So V out is R1 over R1 plus 1 over SC times V in. And V out over V in is your transfer function. Okay? Same with this. Alright? Again, in this case, you have an inductor. V out over E V in is equals to R2 over R2 plus SL. That's all. 8 marks. Let's start. Okay? Any questions? Right, next. Sketch the straight line asymptotic both magnitude diagrams for the resistor, capacitor, and resistor inductor filtering system, filtering circuits, clearly labeling the corner frequencies and the slope of the asymptotes. Hence or otherwise, determine if the output signal of R1C circuit should be used to drive the woofer or the tweeter. Okay, now after you derive the transfer function, you will find that they have different characteristics when you plot it out. Okay, you'll find that they're different. And when you plot it out, you will find that the RL circuit will basically be a first order. But the RC circuit will have a 0 and a pole. Okay, then the question is, if you have a 0 and a pole, the question is, where are these guys? Where are the corner frequencies? Okay, once you know the corner frequencies, then you know what needs to be done. Okay, so that's the tricky part. Okay, I'll show you the solution afterwards. Then the last part, okay, is C. A band pass filtering system for generating audio signals in the mid-frequency range can be constructed by cascading these two circuits, R1C and R2L. Okay, and ensuring that R1C is greater than L over R2. Okay. Sketch the straight line asymptotic both magnitude diagram of the band pass filter, clearly labeling the corner frequencies. So basically it's saying that the mid band must be a band pass like that, right? the mid band. Because the low one is already taken care of for the woofer. The high one is taken care of by the tweeter. So now you're only talking about the mid band. Okay, so what, there will be two cutoff frequencies then. Two. Okay, but it's a combination of the RL and the RC circuit. They're combination. And you're supposed to sketch it out. So after you've done the sketching, the last part is you're given R1, you're given R2, okay, and the bandpass filter should not distort signals between 800 and 3 kilohertz. Design values for C and L. So once you know where the cutoff are, one is based on C and R1, the other one is based on L and R2. You're given R1, you're given R2. One is based on C, one is based on L, therefore you can find C and L. Okay? So those are the parts. Okay, so the tricky part is actually not the low pass, but the high pass, because this is something that may be new to you. So let me put the solution. This is where it is. So this is the RC circuit. Okay, this is the RC circuit. And this is the RL circuit. Now this is straightforward. We've seen this before. 1 over tau S plus 1. Wow, that one definitely is going down like that. Flat, come down. And then the corner frequency is 1 over tau. And 1 over tau, 1 over tau, so this is tau. Sorry, this is tau. L over R2. So L over R2, that's your corner frequency. Okay? Now if you look at this, this is a differentiator here. That means it goes straight up. Remember, integrator goes straight down? Right? 1 over S goes straight down, right? 20 dB per decade. Differentiator goes straight up. We've done it before. Differentiator goes straight up. But at this corner frequency, it will flatten up because the differentiator, which is the 0, and a pole gets it to be flat. That is your pole here. That is your 0, which is the differentiator. So that is that part. And then it flattens here, become flat. We've done it before. It's just that it's new to your eyes right now. We don't talk too much about our friend differentiator. We talk a lot about our friend integrator, but not so much about differentiator. So you would use this as a high pass, right? The high pass filter. This is a low pass filter, right? Follow? Huh? Okay. So anyway, those part A is this, part B is this. Right, haven't done that. This is your mid band. See, this is over here, that is over here. So this is your mid band frequency. Alright, that's what it looks like. So this is 20 dB per decade, 20 dB per decade, this is flat. Then the last part is they gave you R1, they gave you R2, they told you this is 800 Hertz, they told you this is 3000 Hertz, therefore you can find C here, you can find L here. Okay? Which is this part. So that's 800 Hertz, this is 3000. So R1 is known, R2 is known, so C can be obtained from here, L can be obtained from here, and that's your answer. So it's not super confusing, I hope. The only thing is that for many of the students, they don't have that familiarity with differentiator. That's the only thing. But if you look at the expression, it's straightforward. Huh? Okay? All right? Last one. Alright, everybody? Huh? So, we've done 2 past year questions. Some of you only one, because I know some of you didn't come last Saturday. Alright? But I hope that with these 2 you will see the style of the paper. Don't see. Okay? But you will notice there is a certain approach. The approach has always been fairly consistent. Alright? So, I guess this is the last clinic I have with you guys. Your paper is when? 5th of May.
3rd of May.
3rd of May. The second week.
Google Drive.
Alright.
Google Drive.
So, so if you try any other past year question and you're not sure whether it is right or wrong, take a photo and send to me and I will give you my comments. Okay? Can? Just take a photo and send to me. Huh? Sorry? Just send an email with the attachment that you... No, you send me an email with the photo attachment then. Ask me, you point out which part you're not sure. Or you say, oh, I take this question, this is the answer that I got. Can you tell me whether I'm right or wrong? Say yes or no. No, you have to try it, please. You have to try. You know, if you don't try, you won't be able to develop that skill. You have to try. Even if it's wrong, I will tell you why it's wrong. You have to try. Okay? So luckily it's in the second week, so you still got a little bit of time. Second week.
还有别的考试呢，有这学你这科呀？做题我要发给他了啊。
Okay.
我做题发给他 check 了，精心可嘉不？
I guess that's for the end of this clinic for today. So all the best to all of you. So if I
吃饭去，饿死了。
don't hear from you, then I'll see you